All right. Welcome everyone to the 149th meeting of New Directions in Group Theory of Triangulated Categories. Our speaker today is Bill Pützstück from the University of Münster, and he'll be talking to us about completions of wave structures and Anderson duality.
Right, thank you for the introduction and thank you for the opportunity to speak here. So most of this talk is going to be about weight structures. So I want to begin by somehow recalling what weight structures are and what the idea is. So let me also begin by apologizing maybe for my handwriting. It's maybe not the nicest, but I hope you'll be able to read it. So the idea here is that in topology and in homotopy theory in general, we have lots of objects where we have some kind of cellular filtrations. And the point here of weight structures is to somehow abstract cellular filtrations to stable categories. To stable infinity categories. And so let's look at an example of how this works. If you take a finite spectrum, maybe you can think of it like without loss of generality, we can take it to be connective. So you might think of it as the suspension spectrum of some finite CW complex. Then we have a filtration, cellular filtration, which looks as follows. So basically, it's just a filtration, just consists of some maps of spectra, finite spectra in this case, maybe let's do an x2 as well, to xn equals x, which is finite. And basically the point is that we start with, let's say, a finite sum of spheres, because the spheres are our cells in spectra, right? We want some kind of cellular filtration, and if you take a CW filtration and you take the suspension spectrum, you will get a similar thing. And the point here is that the cofibers of these maps in our filtration can also be described as finite sums, in this case of S1. So these are like the one cells, and similarly here the cofiber here, if you take the push out, is going to be a finite sum of S2s, so the two cells. And so we have some kind of filtration, a finite filtration whose associated gradient just consists of finite sums of the sphere. And the point is that this should completely determine the category of finite spectra just based on how the sphere basically works. And throughout the years, there's been many ways of trying to somehow formalize this idea into some kind of a structure on a stable category, or like on just any category. In fact, in the 80s, Waldhausen somehow used something like this on exact categories in his paper on the K-theory, or the algebraic K-theory of spaces. And but today I want to talk about a very specific formalization of this, which is known as the weight structure, and it was introduced by Bondaco and Pogstello independently. Pogstello called them co-T structures, and I think this terminology is used more often in representation theory. So the definition is as follows. We take a stable infinity category, and I'm going to say that a full stable subcategory of somehow connective objects in C determines a weight structure if the following conditions hold. First of all, the idea is that these connectives are basically the objects whose cells are concentrated in degrees 0 and higher, so non-negative degrees. And so it's pretty reasonable to ask that this class of connectives is closed under finite colimits, retracts, and extensions. And then if we have some notion of connective objects, we should also have some notion of co-connective objects. We're in a stable category, so we can just kind of shift. And so there should be a notion of objects whose cells are concentrated in non-positive degrees. So maybe let me do like a little notational side box here. So I will denote less than or equal to 0 as those objects whose basically, who do not have any maps, so X and C, who do not have any maps to one connective objects. So X and C, where let's say pi 0 of the hom from x to y is 0 for all y that are one connective. So if I write this c greater than or equal to 1, I just mean it's like a shift of a connective object. And the intuition here basically comes from the cellular approximation theorem from topology. You know, if you have like some kind of object or like a space who only has cells up to degree n, and you want to map into a space who has cells in degree n plus 1 and higher, then any such map will be null homotopic by the cellular approximation theorem. And this is sort of what this is trying to capture. And now with this, I can state the second condition, which is sort of saying that we have some sort of decompositions for all objects. So for all objects in C, there exists a fiber sequence which looks as follows: x less than or equal to 0 goes to x greater than or equal to 1. And here, this is supposed to be an element of the sort of weight co-connective objects, and this is supposed to be an element of the weight one connective objects. Okay, and at this point, I also want to introduce one more notation, some of the weight hard, which is the intersection of the connectives and co-connectives. And these are basically the cells that I'm working with. I'm trying to build my entire category just from these building blocks. And some of you are probably familiar with the notion of a T-structure and will say, okay, this definition looks very similar to what I know, where exactly is the difference? And one of the differences here is that well, first of all, the orthogonality here is completely in a different direction. In a T-structure, you have no maps from a highly connective thing to a co-connective thing. And also the decomposition here is kind of different. In a T-structure, you would map from a connective cover to your object, and you would map from your object to a truncation. And this is not really the only difference. There are also very qualitative differences, namely that these decompositions here, these are not unique, and also not functorial, which is somehow maybe a bit surprising if you're familiar with T-structures. There it turns out for this to be just automatic by some adjunction properties. But this is not the case here, and the intuition is basically that cell structures on spaces also are not really unique whatsoever, and you wouldn't expect them to be. One more thing, so in the T hard of a stable category T structure is an abelian one category, whereas the weight hard here is an additive infinity category. So right, in some sense it can capture more structure about your category, which we're gonna see soon. Okay, so far so good, but I started this by motivating somehow that we want to talk about cellular filtrations. So given such a structure here on a weight on a stable category, how can I build my filtration? And this is the following construction. Given an object in my weight category, basically I can choose these decompositions now. So I pick one. It's not unique, but I can just take one. And similarly as in T structures, I can just somehow shift my X, take a decomposition, and then shift the whole co-fiber sequence down again. And so this means I can also take a decomposition into like a one co-connective part and a two connective part. And these are of course the same objects. And I would like there to be a connecting map here that makes this top square commute. And what do I need to check for this? Well, essentially I just need to check that this composite here is 0, because then I factor through the fiber of this right vertical fiber sequence. And this is just true by the orthogonality condition that I imposed. Right? So we just define the co-connective objects as having like no maps to one connective, and in particular not to two connective objects. Okay, and so I get such a map, and then I can just do the same thing again. I can get like a sort of two truncation, and I get this, and so on. And continuing this, I get a filtration that I would like to call somehow some kind of cellular filtration, x less than or equal to bullet, together with a map to x. And in fact, you can compute that some of the nth associated gradient of this filtration lies concentrated in degree n plus 1 somewhere with respect to your cell. So by this I just mean like It's an n+1 fold suspension of a thing in the weight hard, which I like to also write like equals 0. And this exactly recovers somehow the idea that we presented in the beginning on finite spectra. Okay. Right. So since I said these decompositions of my objects into like a co-connective and a connective part are not unique, of course, these filtrations will also not be unique. But in fact, so this is not too important for the rest of the talk, but you can show that they're in fact unique as int objects in a suitable int category. But okay, at this point, it's high time for some examples. Yes, also feel free to interrupt me if you have any questions. Okay, so first example, the derived category of integers. So here's a weight structure on this. I claim that this forms a weight structure. To not get confused with the standard T structure, I will probably emphasize this with a W. And the weight connective objects are exactly the usual small connective ones, namely those which have homology in non-negative degrees. And then similarly, the co-connective objects, these should have homology in non-positive degrees, but we also ask that H0 is projective, or since we're working with the integers, this is the same as being free. And then you can somehow, I claim to you that this data somehow forms a weight structure, and you can compute what the heart is. It consists exactly of the additive 1 category, but of course you can also view it as an infinity category of somehow projective Z modules, which you can also just take as like, let me write it like this maybe, arbitrary direct sums of Z, viewed as like a complex concentrated in degree 0. So this, by this notation, I just mean the full subcategory on arbitrary direct sums. Okay, and this restricts, this weight structure restricts to various full subcategories, for example, to perfect complexes, or to complexes who have finitely generated homology in each degree, which I want to denote by this, and so on. And the cellular filtrations for this weight structure basically are just naive truncations of your chain complexes. If you just have some chain complex, you can sort of just chop off the chains in degree 1 and higher, and this gives you some of the weight co-connective part. And then in the next step, you can chop up the chain, like you just set the chains in degree 2 and higher to 0, and then in degree 3 and higher, and this gives you like a filtration in DZ, which I claim is somehow one possible weight filtration you can get from the construction we saw earlier. Okay, next example is a bit more interesting, that of spectra. So here the connective part is again just usual connective spectra, by which I mean those whose homotopy groups and negative degrees are 0. Connective spectra. And then we have the weight co-connective part, which in this case is determined by a homology, right? We're trying to count cells of spectra, so cells are counted by homology, and so we'll say the weight co-connectors are those whose homology, Z tensor X, is you can think of as the homology of your spectrum, lies in the co-connective part of the weight structure we just saw. So these are those spectra whose homology is concentrated in non-positive degrees and has free H0. And then with a little computation, you can check that the weight heart here is in some sense projective modules over the sphere, which again turns out to just be arbitrary direct sums of the sphere spectrum, which happen to be closed under retracts actually, but yes. And again, this for example restricts to the full subcategory on finite spectra, and recovers the example I started this talk with. Okay, and so that this is not too boring, let me also highlight a different example, like one more maybe esoteric example, which is some kind of in some sense we can view it as a dual of the example of the standard weight structure on spectra. So in the following, sometimes I will write spectra ST for the standard weight structure, and here I want to write spectra A and D for the so-called Anderson weight structure. And what is the motivation here? Well, you can see that the co-connective part here is basically determined by homology. And you can ask yourself what happens if we ask the co-connective part to be determined by homotopy instead. So just as the connective part determines the weight structure, also the co-connective part determines it, as long as it exists, of course. And so you could basically ask, well, if I just set the co-connective part, so maybe I call this W prime, to be the following, those spectra which are, or maybe which are T co-connective, by which I mean, so all the homotopy groups in positive degrees are 0, and pi 0 of x is free or projective over the integers, then you can ask, does this lead to a weight structure if I just take the orthogonal connectives? And I claim it does. And the connectives are in some sense determined by the integers. So these are those spectra where the Hom spectrum from the integers, the Hom spectrum, like not just the mapping space, is connective as a spectrum. And the most surprising part about this whole weight structure, and also the thing that gives it the name, is that you can compute the heart to consist of the full subcategory on spectra on arbitrary sums of the Anderson dual spectrum. And when we saw this the first time, and when we were doing this project, Thomas and me, we found this completely crazy, because I mean it's not too important what exactly the spectrum is. Until now, I'll get back to it later. It's the Anderson dual spectrum. Let me just tell you that it's quite weird. So it's for example, it's co-connective. It's like tensoring it with most spectra, will probably result in something rational, except for finite spectra. But for like any complex orientable thing, for example, will be rationalized by tensoring it with this. It's very closely related to the Brown-Commonets dual spectrum, if that tells you anything. It's just kind of a esoteric weird spectrum. And we saw earlier that when we have such a weight structure, then any object in our category has this kind of filtration whose associated graded consists of things in the heart. So this tells you that any spectrum has a filtration whose associated graded just consists of sums of the Anderson dual, which is kind of very surprising.
Can I ask a question?
Yes.
You just said that this is connected to Brown-Commonets. How?
Yes. So there is a fiber sequence IZ Q Almer-McLean spectrum, and then IQ mod Z, and this here is the Brown-Commonets dual spectrum.
Right.
You basically define this one via Brown representability, and then you can take this kind of fiber sequence to define IZ. But I'll get to come to IZ later and give you like a different way to think about it.
I see. So I'm not exactly taking a Brown-Commonets dual.
No,
right.
not exactly.
Okay, thank you.
Yes. Okay. Right. So, okay. So what I want to basically tell you in this talk is somehow how to understand these like infinite weight structures, because classically weight structures have usually in the literature been considered only in the bounded case. So let me tell you what this is and what this means. Given such a weighted category, I can define the weight bounded part basically by taking the weight bounded part. So this just means I take the union of all the weight greater than or equal to minus n intersect greater than less than or equal to n parts, and then I can say that C is bounded if the inclusion of this weight bounded part is just everything. So in this case, like every object has cells only in a finite range. And this is the case that most often appears in the literature, and essentially we completely understand it due to work of Woba-Sosnilo. So there's this theorem of Sosnilo, which essentially tells you that there's an equivalence of the category of bounded weight categories, which you can make this into a infinity category where the functors are like weight exact, so preserve weight connectives and weight co-connectives, and also exact as functors of stable categories. And you can take the weight heart this gives you a functor into additive. Well, let me put a star here. There's some slight idempotent completeness issue I'm sweeping under the rug, but don't worry about it. Additive infinity categories, or like, I mean, yes, everything is infinity here in this talk. And you can also go back, or like by the so-called stable envelope construction. And the claim is that this is an equivalence. So what is this stable envelope? Well, you know, a stable category is in particular additive. So you have a forgetful functor from the category of stable categories to the category of additive categories. And this forgetful functor has a left adjoint. It's called the stable envelope. And part of this theorem is that this stable envelope has a bounded weight structure whose heart is essentially the additive category you started with. Makes sense. You just freely generate a stable category from your additive thing, and everything has somehow cells by or like everything has like a bounded filtration whose associated gradient just consists of the cells, and cells being the objects of the additive category you started with. Okay, so the question I want to investigate here is, what about the unbounded case? And the idea is, or like the question more specifically is, when can I recover an unbounded weighted category completely from the heart? And the idea to solve this, or like essentially the reason this worked in the bounded case, is that we have these filtrations and they're finite, so they somehow converge, and there's no like extent, or like there's no problems with this filtration if it's just finite. And in the unbounded case, of course, our cellular filtrations will be infinite, but then we just ask these cellular filtrations to converge towards our objects for any object in the category. And to make this a bit more precise, I need one more definition. So I want to say a sequential diagram X bullet, which does not need to be this kind of cellular filtration thing, less than or equal to bullet. I want to just say an arbitrary sequential diagram in my weight category grows in connectivity if for all k greater than or equal to 0, the nth associated gradient is of this. Well, I mean, I have a sequential diagram. I can view it as like a filtered object. The nth associated gradient of this is k-connective for large enough n. So eventually, like basically, I'm only adding cells in degrees higher and higher and higher the further I go in my sequential diagram. And of course, the motivating example of this is this cellular filtration diagram. You know, we saw earlier that, let me maybe scroll back. We saw here that the nth associated gradient is n connective, or n plus 1 connective even. And so in particular, this condition is automatically satisfied. Okay. And with this, I can also state the definition of completeness I want to put on a weighted category to somehow force this convergence of my weight complexes, or of these cellular filtrations. So I want to say this weight category C is left complete if the following conditions hold. First of all, we have some hypercompleteness condition that there are no infinitely connective objects. So infinitely connective meaning just the intersection of all n connectives for all n. Yes, this is 0. Secondly, I want to say that C admits sequential colimits of diagrams, of these sequential diagrams growing in connectivity. And third, the connectives are, as a full subcategory of C, are closed under such colimits. So by this I just mean, like, if I have a sequential diagram where every object is already connective, and I know the sequential diagram is growing in connectivity, then the colimit will still be connective. which is very intuitive and perhaps even surprising that you explicitly need to ask for this, but I claim you have to. And dually, of course, there's a notion of right completeness. Z is right complete, and this I just define if C op is left complete. So it turns out the opposite category has a canonical induced weight structure where like some of the connectives in C become the co-connectives in C op, and you maybe know this from T structures. And well, this talk mostly focuses on the left complete case. It's more intuitive somehow. And maybe as a short sanity check, this does indeed force convergence of our weight of these cellular filtrations. So if C is left complete, then if you're getting bored, then you can try this as a short exercise. You can prove that given any such cellular filtration, the way we constructed it before, together with a map to X, if you take the co-limit, you will just recover X. Okay, so, right, let's see some examples of this. So we had some examples earlier. Maybe I can make a small table here. DZ. And then we have left complete and right complete. And okay, so essentially in all of the cases it will be clear that our categories have all co-limits, and in particular these co-limits of sequential diagrams. So the really interesting parts are axioms 1 and 3. I claim 3 can be checked in practice, although in practice this is probably the hardest one, but for expository purposes let me just argue for the first axiom in all of the cases. So the first axiom in DZ, if you remember, the connectives are those who have homology in non-negative degrees, and so the n connectives will just have homology in degrees n and higher, and so in particular the infinitely connective objects would have no homology at all and hence be zero. So indeed, in this case, we have no infinitely connective objects, and I claim you can also check the remaining axioms, and this weight structure on DZ is left complete. And dually, it is somehow right complete. The weight co-connective objects were not exactly those who have homology in degrees 0 and below, but they were included in them. And so if you were infinitely co-connective, you would again not have any homology. So, okay, how does it look for spectra? Well, again, we are left complete because the connectives are just the usual connective spectra. So if we're infinitely connective, then all the homotopy groups are 0, and then, well, we're just 0. However, it is not right complete because, for example, we have infinitely co-connective objects. If you remember, the co-connectors were defined via homology, and there certainly are spectra who just do not have homology. So this would be the infinitely co-connective objects, and it is not 0 because, for example, this contains Ku mod P by, well, chromatic. Okay, how does it look like for the Anderson weight structure? So this was the standard weight structure, and the Anderson weight structure. Well, I already mentioned that a good way to think about it is somehow as some kind of dual of the standard weight structure. And indeed, it will be right complete because the co-connective objects are those whose homotopy groups vanishes in positive degrees. So if you're like infinitely co-connective, you again just don't have any homotopy groups and are 0. However, they're not left complete because if you remember, the connective objects were those where this hom from the integers is connective. And so the infinitely connective ones are those where this hom is just 0. So these are the infinitely connective objects in the Anderson weight structure. And an example of a spectrum in here which is non-zero is, for example, S mod P. So it's in general true that like the sphere does not have any maps from a bounded above spectrum which are like non-rational somehow, and then if you do mod P, it just vanishes. Like all the maps from a bounded above spectrum to the sphere are phantom actually. But yes. And maybe also as like a little sanity check, the bounded weight structures should of course also be sort of orthogonal to the completeness direction. And indeed, finite spectra with the inherited standard weight structure are not left or right complete simply because it doesn't have the required limits or colimits. So for example, if you take the infinite sum of the sphere and shift it higher and higher in each degree, this is in particular an example of such a sequential colimit growing in connectivity, because at the nth step you're just adding an s in degree n, and so it grows higher and higher, and this does not even does not exist in finite spectra. Okay, and similarly also here, again, no, you can just shift them down, for example. Okay, so with all of this out of the way, I can sort of state one of our main results. So this is joined with Thomas, Nikolaus. So first of all, I've now introduced some of the notion of completeness, and of course there's the question of, okay, do these things really occur in practice, and if they not, how can I get a complete thing? Well, I'm claiming that for any notion of completeness you want to have a completion, and this does indeed exist. So there is an initial weight exact, so preserving connectives and co-connectives, weight exact functor to a left or right, both work, complete weighted category, which I'll just denote C goes to C up arrow for the left one, and C goes to C down arrow for the right one. So I mean, you can somehow create a category of weighted categories and a full subcategory of the left complete ones or the right complete ones, and then this will somehow give you a left adjoint to this fully faithful inclusion. And in fact, the hope that we had originally that we can reconstruct under these kinds of completeness conditions and even an unbounded category from the heart is also true. So we get an analog of Vouvazos-Nilus theorem, which is that complete weighted categories there's like a category of them, is via taking the weight hard equivalent to idempotent complete. So it turns out that a complete weighted category is always has idempotent complete heart. The entire category need not be idempotent complete, but the heart will be. Idempotent complete additive categories. And the claim is that this is an equivalence, and the inverse is given somehow. First we do the same one we do in the bounded case. We take the stable envelope. This gives me a bounded weighted category, and then sorry, I need a bit more space, I guess. So I take the stable envelope, and then I left complete it, and then I right complete it. And this construction I want to call somehow this curly K. And why do I call it curly K? That is because of the following result, that if A is an ordinary, by which I mean one category, ordinary additive one category, then you can prove that this curly K construction of A is somehow the suitable infinity category of chain complexes of A, by which I just mean you take the DG nerve of the classical category of chain complexes in A with their chain complex enrichment. And so since, in some sense, the already Verdier called some of the category of chain complexes up to chain homotopy equivalence by this K letter, and this is why we wanted to call this curly K. Curly because we don't want to get it confused with K theory, but yes. Okay, and so in particular, what we recover from this, we saw above that the category DZ with the usual weight structure is actually weight complete, and so we can recover that DZ is actually this K construction of the weight hard. And what was the weight hard? Well, it was exactly projective Z modules, the one category of projective Z modules. So this is some kind of infinity categorical enhancement of this classical statement, about the classical statement, like, the derived category being obtained from this K category. Okay, and I mean the same works actually for any ordinary ring R. So you can put a similar weight structure on the derived category. In fact, there's like a whole, in general, it's like very easy to construct weight structures on presentable categories. Thomas and me have like some result that basically says, okay, if you just have any presentable stable category and a set of objects, you can basically construct a weight structure from it where you say an object is connective if HOMs from your test objects are connective.
Sorry, I have another question. You probably mentioned this just now. I mean, these look very close to, well, not exactly like the classical Hart theorems. Like getting back the whole category. I mean, for like algebraic K theory, connective K theory, or I don't know.
Yes. But I mean, the point is, I mean, there is like Vova, for example, proved like a theorem of the Hart of the weight Hart for negative K groups.
Yeah.
And there's also a theorem that sort of tells you that, I think this is Gillet-Waldhausen, that tells you if you have like a stable category with a bounded weight structure, then the algebraic K theory of stable categories applied to this is the same as the group completion K theory of the weight Hart. And this is somehow actually how you prove that group completion K theory of a ring is the same as the stable K theory of perf of R. But for the unbounded case, I mean, Thomas and me have like some fun computations that we also want to put out. But yeah, I don't think this is...
I mean to say your work with Thomas, like if you just go up a little bit, right, so these are not, I mean, these can't be generalized to recover any of those classical Hart results, obviously.
No.
Right.
This has nothing to do with
different. Yeah, that's very
yes.
Sorry. Yeah.
No, it's okay. Okay, and I also want to make a remark that somehow this reconstruction result from the Hart is completely like this part 2, that like a complete weight category is essentially determined by the Hart. This fails completely for T structures. For example, if you look just at the forgetful functor from DZ to spectra, this preserves limits and colimits. It is T exact. It also is an equivalence on the T Harts, both of which are just abelian groups. And the source and target have complete T structures. Nevertheless, this functor is very far from being an equivalence. And so somehow, and I interpret this in a way that somehow, basically my interpretation of this is that for T structures, the Hart is an abelian 1 category, and like a 1 category just cannot capture enough information about your category, whereas in a weight structure, the Hart is just an additive infinity category. For spectra, it consists of sums of the sphere, and of course a lot of information is in the sphere about spectra. So weight structures really give you even the possibility of having such reconstruction results. Okay, let's look at some examples for these completions. So,
sorry.
Yes?
I have a quick question.
Yes?
Do you hear me?
Yes, I hear.
About your settler results, do you need weekly idempotent completes, or
well, it follows from
you
the
want
idempotent
completes?
Yes. I mean, I need idempotent complete, and this implies weekly idempotent complete.
So
yes, in the bounded case, you only need weekly idempotent complete, but in the complete case, you need
in this case, you need you cannot generalize to the weekly idempotent completes, right?
It's just because like, well, I mean, I can generalize this functor, of course, but it just won't be an equivalence because the Hart of a complete weighted category is always idempotent complete.
Okay, and I'm not sure of the precise definition of complete weighted categories. Did you need assumption of idempotent completes?
No. I don't need an assumption. I mean, the definition is just the one I said here. Like, so complete just means left and right complete, and left complete is this. And I claim it actually follows that the connective part of this will be idempotent complete. And And then also the co-connective part in the complete category will be idempotent complete. There's like a weird issue with the entire category. It doesn't have to be idempotent complete, but some of the bounded. If you're bounded in one direction,
Okay.
then this part will be.
Okay.
Yes.
Thank you.
Yeah. Okay, so let's look at perfect complexes. So this is of course the bounded category, and if I left complete it, then maybe it's not very surprising that I get somehow complexes with finitely generated homology that are bounded below, right? I mean, perfect complexes are already bounded below, and then the idea is that I just spread it somehow towards positive infinity via this left completion. And similarly, I can sort of spread it with a right completion towards negative infinity, where I now get complexes with finitely generated homology in each degree, but they're bounded above. And you know, I still don't really allow infinite or like countable sums in one degree. It's really only the spreading out that you do. And it turns out that if I somehow complete in both directions, then this always commutes. So left and right completion always are compatible. It's a general fact. And I end up with just arbitrary complexes with finitely generated homology in each degree. Okay, and of course, I mean, here I also have like this is now complete, and I get a reconstruction result that this is just this K category for finitely generated projective Z modules. Yeah, for this one classical additive one category. Okay, a more interesting example is that of spectra and the two weight structures we saw. So I have, if I start with the weight bounded part, remember this is not like finite or anything, it's just arbitrary spectra whose cells only sit in a bounded range. So I can still have like, by Vogasov-Snilos theorems, this is the stable envelope of the weight heart, which consists of arbitrary sums of the sphere. Then, you know, we saw that spectra as a category is left complete. So it's maybe, again, not very surprising that here you get bounded below spectra if you left complete it. It's a full subcategory. Yes. And if I now right complete this, it is not so clear what I get. You know, we saw this cannot be spectra with the standard weight structure because spectra with the standard weight structure is not right complete. We saw earlier that it has infinitely co-connective objects because there are spectra whose homology just vanishes. And similarly, now comes one of another surprising fact. So it turns out that this category, the stable envelope, is just the same as the stable envelope of the category of arbitrary sums of the Anderson dual. This is because the hom of IZ, or the endomorphisms of IZ, are just a sphere. And then you can somehow, you need a bit more, you need to work a bit harder to somehow extrapolate this to arbitrary direct sums. And then you can in fact already prove an equivalence of additive infinity categories. And you take the stable envelope. And so you get this. And this was by definition the weight bounded part of the Anderson weight structure. It's W prime. And the Anderson weight structure was right complete. So it's maybe not surprising that if I right complete this part, that I end up with weight bounded above things in the Anderson weight structure, which are just by definition T bounded above spectra. You know, the weight bounded above or weight co-connective in the Anderson weight structure just means homotopy groups are non-positive and pi 0 is free. So just weight bounded above just means T bounded above. And again, I can ask myself, what happens if I now left complete this? And again, I know that I just cannot possibly end up, or like maybe I should draw this. So since left and right completion commute, I know that I will end up at the same spot. However, I also know that this is not the Anderson weight structure, because the Anderson weight structure is not left complete, and whatever I get, it has to be left and right complete. Okay, and so the mystery is somehow, okay, what is this funny category I get as a weight completion of the category of spectra, either with the Anderson or the standard weight structure? And this is the next theorem. Again, joined with Thomas, of course. So let A be the spectral integral Steenrod algebra. So the endomorphism ring of Z in spectra. It's co-connective, has like integral Steenrod algebra and negative homotopy groups. And the first claim is that if I take the standard weight structure on spectra and I just take homology, then I can land in left modules over A. The endomorphism ring, of course, acts on Z, and I can just act on this left part here. And so this functor into dz actually canonically lifts to left modules over the Steenrod algebra. And the claim is that this is a weight completion. And okay, I didn't exactly tell you how the weight structure on left modules looks like, but it's going to be basically the connectives are just underlying connective. It's going to be generated in a certain sense by A. And so like a weight connective object in here is just an underlying a module which is underlying connective as a spectrum. And a general fact about these weight completions is that because spectra with the standard weight structures was already left complete, you get for free that this functor here is fully faithful on bounded below objects, which is maybe a bit surprising. At least it was to me. I have not dabbled in lots of computations with the Steenrod algebra. And in fact, you can somehow identify, so of course you have like a right adjoint here, where you take like hom in A modules out of the integers. And the unit of this adjunction is the following. So it's x by definition, it goes to hom A mapping out of Z into Z tensor X. And somehow part of our proof identifies this unit with a canonical map of X into the following limit. Which is, well, I would never be able to guess this identity here, this hom in left modules over the integral Steenrod algebra, but it happens to be this. And from this description, it's a bit more easy to see that this map will be an equivalence for bounded below X. So X to this limit, if X is bounded below, you can just pull the limit through.
Sorry, I mean, I can see, so it is not fully faithful on the whole thing. It is fully faithful on a is this the maximal full subcategory on which it is fully faithful?
Well, it's somehow, in fact, it will be an equivalence on hom spectra whenever the target is bounded below.
Right.
But yes, I mean, I think that's it. I mean, we just saw that there's just a lot of spectra whose homology just vanishes, like Ku mod P, and so this will just be 0, and there's just really no chance if you're not bounded below. This is essentially because bounded below things are automatically Z local.
Right, and also I don't want to of course you will probably write this just now. So the completion with respect to the Anderson T structure and the completion with respect to the weight structure.
Yes.
And the completion with respect to the other standard weight structure, there isn't any intuitive obstruction for them to be not equivalent. The completions could be equivalent with the weight structure still being very different, right?
Yes, exactly.
Yeah.
Yes, exactly. I mean, the whole point is that they really are equivalent. I mean, the left and the right weight completion, they commute. And it turns out by this equivalence here, this is a weight exact equivalence. And so we start with the same bounded weighted category. And then we do left, right, or right, left, and it doesn't matter really where we, the order doesn't matter.
I understand. I mean, I guess I should ask you this later.
Yeah, we can maybe talk about it later.
I mean, the point was, I wanted to see what was special about SP here. What couldn't be replicated with others. We can, anyway, don't ask this up.
Yeah, we can talk about it later, but spectra is not particularly special here, yes. Okay, so as a second point, we now get somehow if X and Y are bounded below, then you can just take the X spectral sequence you have in any category of of modules over a ring spectrum, pi star A, ST, over like the homology of X and Y now, X and homology of Y, and usually of course this converges to the hom in the module category, but since we're fully faithful on these guys, we just converge to the usual hom spectrum between X and Y. And it turns out you can, with a little bit of algebraic work, you can identify the abutment and the E2 page with the integral atom spectral sequence, but we somehow claim that we can actually identify the entire spectral sequence with the identified with the integral atoms spectral sequence. It's maybe a bit surprising. And maybe this answers also your question, Roderick, but of course, we saw above that the left and right, the weight completion of the Anderson and the standard weight structure have to be the same. But in fact, somehow what pops out of the proof that we do is that this functor, taking somehow hom out of the integers, from Anderson weight structure to right modules over A is a weight completion. But we know that the weight completion has to be the same as the one for the standard weight structure. So it turns out there is an equivalence between left and right modules. And this is essentially because you can somehow a posteriori justify this by saying, okay, our ring spectrum A is a ring spectrum with involution. And the involution comes from Anderson duality via Anderson duality. Okay. Right, so this was basically what I wanted to tell you about weight structures, and we have these nice construction results. And now in the last few minutes, I want to maybe make a little cut and talk a bit about where all of this sort of came from. So originally, Thomas and me were working on a project, and I mean, we're still working on this, condensed Anderson duality. Somehow this weight structure project only originally arose as some kind of side project. But yeah, okay, so what is the short version? So maybe let's talk a bit more about Anderson duality. So the way I like to think about it is that you have the canonical Z-linear duality on dz, where you just hom into the integers. And dz, of course, has forgetful functors to spectra. And I claim that you can make a filler here where you just hom into the Anderson dual spectrum. And in some sense, this uniquely characterizes the Anderson dual spectrum, like by somehow making this diagram commute. So in particular, let me write izx as somehow hom from x into iz. This gives you like an interesting duality on spectra. And in fact, for example, you can compute that iz of the integers is just z. This follows by the commutativity of the square. And for example, you can also compute iz of big Ku is again just big Ku. And there are some other spectra which have some kind of interesting Anderson duals. But this was actually the reason that Anderson originally introduced this to somehow prove some kind of universal coefficient theorems for complex K theory. And if you dabble a bit with this, then it's not very hard to prove that, as for any duality, you always have a map into the double dual, and this map is an equivalence if and only if the homotopy groups, or let's say X is a spectrum whose homotopy groups are finitely generated in each degree. So if this is the case, if X has only finitely generated homotopy groups, then it's very easy to show that this map is an equivalence. The converse, surprisingly, I could not find anywhere in the literature, so I think we're the first to prove this, and it's also a bit finicky. You really have to get in some nasty X calculations with this, but it just happens to be true. And so, of course, this is kind of limiting, one application of this is somehow that if X and Y are somehow Anderson dual, then you can compute the hom from X to Y by computing the hom from the Anderson dual of Y to the Anderson dual of X. And then if you have some kind of self-Anderson dual spectra, then this might simplify some kind of computations. And we would like to extend this to all spectra. And the idea here to do this is to somehow take inspiration from Pontryagin duality, from classical Pontryagin duality. How does this work? Well, Pontryagin duality somehow tells you that for a locally compact abelian group, I guess, somehow you have this kind of similar duality going on, and it works really well because you take into account the topology. The problem here is that if you if you take like, you want to take the Anderson dual of like an infinite sum, then you get an infinite product, but you don't really have any product topology on here, like in topology, so it's kind of uncontrollable. And the fix of this in these modern times is to work in condensed spectra. And so the idea is we take the Hom in condensed spectra from well, any condensed spectrum into the discrete Anderson spectrum. By this underline, I just mean, you know, we have like a fully faithful embedding of spectra into condensed spectra. If you like to think of condensed things as some kind of sheaves, then this is the constant sheaf embedding. And this here, this somehow topological or like condensed Hom is supposed to be now my keep track of the topologies. You know, even if X is a discrete spectrum, then the internal Hom in condensed spectra certainly can carry a topology, similarly to how like the mapping space between two discrete spaces need not be discrete. And the idea is that you can leverage this topology to really prove a much more general version of some more Anderson duality. And the theorem is that we were able to show is that for X in spectra, for any spectrum, no restrictions on the homotopy groups. Sorry. For X in spectra, the canonical double dual map, you know, let me maybe not write condensed every time, into the double condensed Anderson dual is an equivalence. So, you know, this here is not discrete anymore, but somehow the double dual turns out to be discrete again, as we might know from von Triagen duality, and so you can somehow check that this is an equivalence in general, and it's a nice extension. And what we wanted to do originally, so we can also in fact also version for condensed dz, where you take the z-linear duality. Turns out, like, if you take any complex in dz, the map to its double condensed dual into z will be an equivalence. And originally, we wanted to somehow understand this category of reflexive objects. So this property of the map into the double dual being an equivalence is called reflexivity, and we wanted to understand. Well, yeah, maybe let me not write this. I have maybe 2 more minutes. I guess we started a bit late. So we wanted to understand some kind of this category, this subcategory of condensed spectra on the reflexive people. And of course, this map is natural here, and both sides commute with like finite limits and colimits, so this is going to be a stable subcategory. We have not completely been able to do this for spectra yet, but we have done this for dz, where things are a bit more simple. And the proposition here is basically that in condensed dz, in fact, all of this is happening in solid dz, if you know what this is. We have the following somehow equivalence of subcategories or equalities of subcategories. First of all, you have the thick subcategory generated by those x and somehow the condensed z-linear duals of x, where x is any object in dz. This is the first category. Basically, we want to understand, we know any discrete object is reflexive. Of course, the dual of a discrete object is reflexive. So let's see what is really the stable category generated by this. And it turns out that you can describe this as those x in condensed dz where there exists a fiber sequence. Oh, sorry for my handwriting. Fiber sequence which looks as follows. We have like a dza goes to x goes to b, where like a, b are just discrete. So anything in this thick subcategory is a single extension. A priori, I could take extensions and cofibers and finite limits and whatnot, but it turns out every object in there is just a single extension. And this might be familiar for you if you know these kinds of Tate categories. So the Tate category of a stable category is some kind of full subcategory of int of pro generated as a stable category by the int objects and the pro objects, and then you can somehow prove a posteriori that any object in there is just a single extension of a pro object by an int object. And we wanted to describe this, but we saw that somehow this cannot really be just Tate, because there's also theorems that Tate does not actually embed into condensed complexes. But it turns out that if you can weight complete this. It turns out that if you have any stable category with a weight structure, then Tate inherits a weight structure. And if you take the both left and right weight completion, then this recovers this funny category of somehow reflexive condensed complexes. And in particular, this is complete in both directions. So it's an example of this K construction. And what do we have to put in the middle? Well, we have to put the heart, which consists just of arbitrary sums of Z and arbitrary products of Z, where the product is taken in condensed. So it carries some kind of topology. And I think this is a really nice, somehow intuitive description of this category, or an intrinsic description of this category. So for example, Drinfeld considered these kind of Tate vector spaces which basically consist of these additive categories, where instead of Z you use a topological field, and then you have interesting dualities going on. And, right. So in some sense, the entire weight project just came from wanting to describe this category. And I thought it's kind of fun to somehow just build this whole theory out of this. But yes, this is what I wanted to say. Thanks for listening.
Thank you, Phil. Let's all give the speaker a round of applause now. Okay, if you have any questions for Phil, please ask them.
Excuse me?
Yes.
I have been considering a question relevant with large weight structure. Yeah, I'm not sure if you consider this. So the setting is consider a presentable stable infinite category with a accessible T structure. And my question is, when is this connective part forms a large weight structure? Yeah, and one sufficient condition I figured out is when the projective object in the connective part generates the whole category as a localizing subcategory.
So,
but
wait, sorry, I need to write. So you have C is stable, presentable, and you know that C has a T structure.
Yeah, accessible T structure.
Accessible, okay. And the question is when is this the connective part of a weight structure?
Yeah, exactly.
Okay. I have not thought about this, but I know, in the compactly generated case, I think there's some results on this, but I think in general, I do not know. I guess, well, if it's only accessible and not, by accessible, do you mean filtered colimits or kappa filtered for some kappa?
It's, the connective part is presentable. That's the
okay.
accessible, yeah.
I see. Well, I suppose certainly you would want the weight structure to be also left complete, and then we have a general result that if you have a left complete weight weight structure, so if C is left complete, then the weight connective part turns out to be freely adding geometric realizations to the weight heart.
Yeah, exactly. And the weight part can be identified with projective object in the connective part.
Yes. And it turns out that if you there are some conditions on when this is presentable. So it turns out, so there's this notion of sumpactness. So you can how you can ask for compact if you commute with filtered colimits. You can ask for sumpact if basically any map into a big sum factors through a smaller sum. And then if you're projective and sumpact, you are compact. And I can prove that somehow if you have an additive category which has enough sum-packed objects, like it's like sum presentable or some analog of this, if you have enough sum-packed objects which generate under like sums and stuff and retracts, then p delta of it will be presentable. Yes, I talked with Vova Sostilo about this.
Yeah,
yes.
this is correct.
Yes.
Yeah, but I'm not sure if your connective part satisfies this condition, is it definitely weight structure?
Sorry, can you repeat the question?
Yeah, I mean, if your connective part is like this, projectively generated, does that guarantee it forms a weight structure?
Well, I mean, you can always just you can like stabilize. I mean, it does give you a weight structure, I guess. So you can take the stabilization of p delta, the Spanier-Whitehead stabilization, and this is the same as if you took the stable envelope of the heart and somehow left complete it, and this will be a full subcategory of C, in fact, of the bounded below part. I'm not sure. I guess then the question really is if this is like an equal. And then you can somehow ask about, okay, what happens at minus infinity? But I don't know. I don't know in general. No, sorry.
Yeah, okay, don't worry. Nice thought.
Yeah.
Thank you.
Thank you, Jason. Any other questions, anybody?
Hello.
Hi.
Okay, yeah. So I have two very basic questions probably. So one question is, I mean, at least in the standard weight structure on the category of spectra, you have that the connectives are also closed under all colimits, right?
Yes.
So is that generally true, or I mean, because I think in the definition you only require finite colimits, right?
Yes, I only require finite colimits, and in general, it's wrong. I mean, this is also part of the definition of let completeness requires somehow a few more colimits to somehow like the connectives to be closed under a few more colimits, like these sort of sequential diagrams growing in connectivity, but this can really fail. Like, for example, in the Anderson weight structure, you can just check that not only do you have like infinitely co-connective objects, there are also just sequential diagrams growing in connectivity where each object is connective, but the colimit will not be connective or even bounded below anymore. I have like concrete examples of this in the paper. In fact, like I probably have like counter examples for any statement you can imagine in the paper. There's actually lots of examples in there. It's kind of fun, but yes, it's very bizarre somehow. Yeah.
Okay, thank you. And one more question. So if I understood correctly, so we know that if we look at, I mean, we know that the standard weight structure on spectra is not right complete. So can you describe somehow the completion? I mean, is it also
yes,
some
this was the
category
theorem.
of
The right completion is the left modulus of the integral Steenrod algebra.
Okay.
Yes.
Thank you.
No problem.
Thank you, Julia. Any other questions? Can you go to that last duality statement?
This one?
Yeah. So the version for cond dz, I mean, is the proof very different?
No, it's the same. And in fact, actually the same, like the result just works for, if you know what a dualizing spectrum is, in the sense of Lurie, it works in this generality.
Right.
You just, like, it turns out, like, Z is a dualizing object, is like a dualizing thing for Z, and IZ is like a dualizing thing for the sphere, and then in general, if K is a dualizing thing for some ring spectrum R, then you have a similar statement in condensed R modules.
Yeah.
Yes. But I mean, originally we were only interested in Z and Anderson duality. I mean, somehow because of this relation. I mean, the same relation will keep being true in the condensed world.
Right.
And you can somehow bootstrap, actually. You can like prove things in DZ and then deduce things for Anderson duality, actually.
Right.
From this. Somehow you really heavily use somehow compatibility with the T structure and with the weight structure of some of these functors, and you can somehow always bootstrap into like things being concentrated in 1 degree, and then you reduce to somehow the integral duality.
And one comment, this is not, this really can't be a question. So in algebraic geometry, there are cases where like there is a big category with a standard T structure, and then you look at certain full subcategories of that big category. Well, everything is stable, and there are cases where one can ask the question that if the full subcategory that you're looking at has a T structure as a non-trivial, like a non-degenerate T structure, under what circumstances can one say that just the existence of a non-degenerate T structure on that guy forces that category to have a restriction of the standard T structure on the big guy itself? So, for example, this is known for perf and QCO, with the extra assumption that the T structure that we assume to exist on perf is bounded. Well, also need this scheme to be a finite dimension. In these cases, like from my experience with weight structures, because very fundamentally, the normal one categorical proofs almost always use some filtration tricks, and because you don't have that uniqueness, often quite a lot of things fail.
Yeah, I know
And
the
I don't really
statements
know.
you're talking about, but I'm not sure if
Yeah,
there's like a similar unicity. I mean, I would look in the work of Bondarco. He's been thinking, I
of
mean,
course.
he really
Yeah.
does a lot with like weight structures on QCO and stuff. And
Yeah,
there's a
yeah.
lot of theorems of Niemann which also like allow you to prove things like this. Niemann has this, what was the name?
The preferred equivalence class?
Yes, but he actually has some like theorems which allow you to, like, he doesn't call them weights, like he doesn't ever mention the word weight structure, but he has like some results which which basically characterize when you can build like a weight structure on like QCO with what kind of,
Yeah.
I mean, they will not be like actual weight structures, there will be some kind of weak version.
Yeah.
And in fact, the entire paper with Thomas is written in like for like weak weight structures, where you somehow, one way to view them is like, if you know this paper of Ishan and Vova.
Yeah, C structures one, yeah.
C structures, like a hard structure of cohomological dimension n is in particular the same thing as a weak weight structure of some like n, and all of these cases are covered by our paper. You can run the whole theory for that. In fact, you can somehow, okay, I think I'm going on a tangent here, but I mean, the fact, I do not know any like unicity results. I mean, in some sense, for complete weight structures, you know that the weight hard completely determines it, but not, I mean, I don't know any results of the kind that you mentioned for the T structure case.
Yeah, I mean, and also, I mean, with perf, you can uniquely determine QCO, but to be very, very careful, like if you wanted to look at what was exactly being used, I mean, outside the stable infinity terminology, it would come down to the fact that perf would have a unique enhancement and like those kinds of things.
Yeah.
So if you replace perf with something else, there are lots of categories for which one knows that due to the work of like Stellari and Kanonako, like lots of like algebraic geometers, that the existence of unique enhancements are fine. And there was a big paper by Ben and Tiao it's still a preprint because it asked quite a lot of questions, and then these people solved those questions, and I think Ben didn't want to. Anyway, so yeah, I mean, this is something, it's very interesting. Thank you. Sorry.
Yeah.
Anybody else wants to ask?
Yeah, I have a question about the last slide. Possible? Yeah. So this state of perf, this embeds into condensed DZ, and this is a subcategory of int of pro of perf. Is it in general true that int of pro of perf is a subcategory of condensed DZ?
No, and so this is the thing I wanted to highlight. So Tate does not actually, it does not embed into condensed Z. You have to, I mean, there's this paper by, sorry, I hope I don't mess up the names, Melani Porcelot Vezzossi, which prove that a version of Tate embeds, but in fact, actually, like you have to like bound things. If you allow unbounded, like filtered collimate are going off to infinity and going off to minus infinity, then things, their proof breaks. And in particular, int of pro will not embed. But somehow, if you just naively write, you definitely have a canonical map from int pro to condensed. And if you have like 4 cases where you can check the hom, you have like int, pro, int pro and pro int, and 3 of those will be fine, int pro pro, and I don't know one of the int pros and one of the pro ints, but the other one won't be. But yeah, I mean, in some sense, this here generalizes their result a little bit, because this category you have here with the weight completion is a little bit bigger than what they can embed into condensed DZ. In fact, you can also you can write this as Tate of perf, where you mod out not perf but DZ finitely generated. You have to mod out a little bit more somehow, but it turns out this you can write it as this Verdier quotient as well. There's like a lot of descriptions of this category. Yes.
Cool. And then one last thing. So you had the result that for discrete spectrum, the double Anderson dual
Yes.
is itself again.
Yes.
What happens if you take a finite spectrum and instead of the Anderson dual, just take the sphere spectrum, the discrete sphere spectrum?
Oh yeah, I mean, well, if X is a finite spectrum, then it's dualizable, and for any dualizable object is reflexive. So like, if we're just taking normal Spania-Whitehead duality.
Oh, sorry. I mean, if X is an arbitrary discrete spectrum, but then in place of.
Oh.
But in condensed, you do the
No,
internal homes to the sphere spectrum.
Yeah. No.
Do the same arguments work, or
no? It
no?
really
Okay.
does not work. I mean, in fact, somehow the Spania-Whitehead duality on spectra is already extremely finicky, and you know, if you like thinking about things like this, I can challenge you to come up with an spectrum X, so that the map into the double Spania-Whitehead dual. So this is, you know, like hom X sphere, where this is always the hom spectrum. You can find a spectrum X for which this is true, where X is not finite, but it's really not easy to find. So I tried to prove at some point, because in this Anderson paper we also look a bit at like sphere reflexive things, because I thought it was kind of cool. And first I was convinced that it's only finite spectra or only dualizable spectra can be reflexive, but after like a week or 1.5 weeks of trying to prove this, I came up with the following example. And I'd be very curious to see if there are more. So you can take the sum over all primes of the sphere mod P shifted down by P, and I claim you can check, well, obviously this is not a finite spectrum, and I claim you can check it is actually reflexive, but it's very, very crucially uses somehow all primes, and I have no idea whether this is possible at a single prime, and in general, like, hom into the sphere, even in condensed world, it just behaves very weirdly. Like, it's very hard to understand to me. But I'd be very interested in it, yeah.
Thank you, yeah.
Also, well, Pützstück has 2 Zs and 1 S.
What? Sorry?
Just now you're writing the name of Gabriele.
Oh.
I think it's 2 Z and 1 S.
Ah, okay.
It's okay. It's okay. Yeah. This is the paper that's titled Tate modules as condensed modules.
Exactly.
Any other questions? Anybody? Well, if you don't have any more questions, let's thank Phil once again. Can you send me these slides afterwards?
Yes.
I mean, the notes afterwards.
Okay, I'm not sure. I mean, is it? Yeah, I'll try. I have some problems with exporting slides on OneNote. Maybe I